Good afternoon to all. My name is Venkat Niranjan. I am from BTech final year and we did a project on a three-phase dual output T-type three-level converter, and these are my batchmates Reshma Banu, Vamshidhar, Parshram, and under the guidance of Mr. C. Ganesh sir, Assistant Professor, Department of Electrical and Electronics Engineering. And these are the outlines: aim, introduction, what is T-type three-level converter, circuit diagram, comparison, switching states of dual output T-type three-level converter, sinusoidal pulse width modulation techniques, waveforms, and why use a 3 T-type 3-level converter, types of 3 T-type 3-level converter, advantages, applications, and results. The main aim of our project is to generate two outputs from a single input by using a three-phase dual output T-type 3-level converter. And in recent years, dual output power conversion systems have been used in wind power generation, UPS, dual motor drives, and power conditioner. Dual output converter is the key, including the dual parallel converter, the 5-level leg inverter, and 9 switch converter. Some of these topologies reduce the cost and volume of the system by saving the switches, and studies show that they can reduce the switching losses and improve efficiency when operating in identified requirements. And what is a T-type 3-level converter? T-type 3-level converter is a type of converter that can generate two outputs from a single input. It uses three levels of voltage to achieve this. Hence the name. It's a popular choice for renewable energy sources, electric vehicles, and industrial applications. And this is the circuit diagram of proposed dual output T-type 3-level converter. And here we can give the DC supply and we get the AC supply, and this is the inverter circuit. And here we give only single input, and we get three we get two AC voltages, that is three phase AC voltages. And these are the three legs. This is the leg 1, this is the leg 2, and this is the leg 3. And these are the S3 S3 dash, and these are the bidirectional switches. And in each leg there are 4 switches connected, and this is the O, this is a neutral point, and this is we have two capacitors, upper capacitor and lower capacitors, to balance the voltage. And this is the comparison of various dual output T-type 3-level converters. And in recent years we used different converters as compared to proposed dual output T-type 3-level converter. When compared to other converters, the main difference is switch number, clamping diode, bidirectional switch number, uh, clamping diode blocking, switch or bidirectional blocking, etc. And here the main use of these converter is this, when compared to other converters, is to reduce the switches, clamping diodes, etc. And these are the switching states of dual output T-type 3-level converter. And here we have figures A, B, C, D, E, F. And in figure A, and we get the output voltage VO equals to VD by 2 and VXO as VD by 2. And as shown in figure B, we get VO as VD by 2, VXO as V0. And in figure C, VO equal to VD by 2 and VXO equal to minus VD by 2. And in figure D, VO equals to 0 and VXO is equals to 0. And in case of E, VO equal to 0, VXO equal to minus VD by 2. And in figure F, we get VO as minus VD by 2, VXO as minus VD by 2. And here we got the upper output three-phase sinusoidal modulation waveforms, VMA, VMB, VMC. And these are the lower output three-phase sinusoidal modulation waveforms. And these are the plus offset and these are the minus offset. And where omega 1 and omega 1 2 are the fundamental angular frequencies, and phi 1 and phi 2 are the initial phase angles, and m1 and m2 are the modulation indices, are the linear range is 0 to 1. And here offset 1 and offset 2 are the DC offsets, and the values are 1 minus m1 and 1 minus m2 respectively. From equation 1 and 2, the output line voltages are affected by the DC offsets in the modulation waves. Therefore, the maximum peak value of the output line voltage is 0.866 VD. And these are the relationship between the switching states and the phase voltage. And this is the figure is described for the upper output three-phase waveforms. And here in this case, omega 1 and omega 2 equals to same, and phi 1 and phi 2 also same. Therefore VMA and VMX of the AX leg are the common carriers as shown figure. This is the VC1, this is the VC2, and this is the VMA, and this is the VMX. And here if VMA is higher than the VC1, the upper output voltage is VAO is VD by 2. If the modulation VMA is smaller than the VC2, the upper output phase voltage VAO is minus VD by 2. Otherwise VAO is 0. According to the same process, when the modulation wave VMX is higher than the VC1, the lower output phase voltage VXY is VD by 2. When the modulation wave VMX is smaller than the VC2, the lower output phase voltage VXY is minus VT by 2. Otherwise, the phase voltage is VXY is 0. And this is the figure 2 when omega 1 and omega 2 equals to same but phase angles are not equal. So this is the figure shown VC1 and VC2, VMA and VMX. In this figure, phase angle is different. So this is the displacement angle between the VMA and VMX. So phi1 minus phi2. The duration is, the angle is 0 to pi. In this range the phi can vary. Here according to the modulation constraints, the VMA is always higher than the VMX. This is the VMA and this is the VMX. VMA should be always greater than the VMX. And figure 3 shows that when here omega 1 and omega 2 are not equal, here modulation range means m1 plus m2 should be 0 to 1. Then the modulation waves Vm and Vmx of AX leg and the common carrier shown in figure. The modulation index m2 is less than 0.5 and the DC output offset is added, resulting in the modulation wave Vmx always smaller than the Vc1. And these are the result waveforms which we got. And in this case, see, this figure shows the f1 f2 is same frequency. We are applying same frequency, but m1 m2 equals also same. Here see, when frequency same and modulation index equals to 1, here we have many voltages, means amplitude and magnitude are increasing when frequency and modulation index is 1 and frequency is 50 Hz. These are the line voltage VXY and load current IABC and load current IXYZ. These are the voltages, upper one, these are the lower one, these are the currents. Here when we give the same frequency and modulation is equal to 1, this means magnitude and amplitude are same and we have the different levels, means levels also increasing. And here frequency is same, f1 f2 equals to 50 Hz, but m1 m2 equal to 0.6. When compared to before diagram, here modulation index is 0.6, means the level of the modulation index is reduced. When the level of modulation is decreased, then the magnitude and current also decreases. And these are the voltages, and the upper one are the voltages and lower one are the currents. Here levels also decreased when the modulation index is decreased. And here the figure shows this figure frequency is same, but here frequency we are giving same both, that is 50 Hz, but for this figure we are giving m1 equal to 0.6, m2 equal to 0.3. These are the upper one is the voltages, lower one is the currents. Therefore here if we see VAB and IABC, here VAB, here frequency is same but m1 is equal to 0.6, so here modulation index is reduced somewhat, so magnitude and current also reduce, the levels of the voltages and current also reduce. In the similar manner, when compared to when m2 equal to 0.3, the levels of the voltage also reduced, the magnitude and current also reduces. And this is the figure. Here we are giving two different frequencies, f1 as 50 Hz and f2 as 100 Hz. Here m1 as 0.4435 and m2 as 0.5. When we are giving f1 equal to 50 Hz and m1 equal to 0.4435, then we get the m1 is 0.4435, so the m1 is modulation index is reduced, so magnitude and current of the voltage and current both will be reduced. When m2 is 0.5, here the voltage and current also same, it also reduces, levels and magnitude and amplitude and magnitude of the currents also reduces. It mainly depends on upon the modulation index, the means amplitude and magnitude of the current and voltages. And we have how does a T-type three-level converter work and a types. Here we have many types, means single phase and three phase. Here single phase we can use for lower applications, three phase is for higher power applications. These are the simulation parameters which we got: DC link voltage, DC link capacitor, resistive inductive load, carrier frequency, dead time, power MOSFET. DC link capacitor voltage balance have the following assumptions are made. How we can make the DC link capacitor voltage balance? The total DC link voltage is constant, which can eliminate the influence of the DC link voltage ripple on the neutral point voltage. The DC link capacitors have the same capacitance and characteristics, that is upper capacitor Cu equal to Cl equal to C. Two sets of the load currents are sinusoidally symmetrical. The carrier frequency is much higher than the fundamental frequency, so the modulation waves and the load currents are considered as constants within a carrier period. The advantages are here. Here we have smaller size and weight, double the power output of traditional converters, more efficient, it generates less heat, low harmonic distortion, better voltage regulation. These are the applications of T-type three-level converters. We can use in renewable energy systems, we can use electrical vehicles. Here we can use in applications in when comes to electric vehicles, in that we have front wheel and rear wheel. So by giving the single input and we get two outputs, these two outputs we can give from one for front wheel, another from rear wheel, that it can save the cost of the motor and design, and it can be used in drives also. These are the future developments. The T-type three-level converter is still a relatively new technology and there is room for further development. One area of research is improving the switch frequency to reduce the size of the components. Another area is exploring its potential for high frequency applications. Conclusion: the voltage imbalance mechanism of the DC link capacitors was revealed, and the method to realize the capacitor voltage balance was proposed, which solves the problem of voltage imbalance. Finally, from simulation results, confirm the topology and the effectiveness of the modulation scheme to control the output voltage and capacitor voltage. Therefore, it is recommended that for the applications with the directional power flow, such as multi-motor drives and multi-phase machine drives. Thank you.